Hi everyone, my name is Pranati. I'm your host of Under the Microscope, and today we have with us Antonio Manesco, who is a postdoc at Delft University of Technology in the Netherlands. Hi Antonio, how are you? Welcome to Under the Microscope.
Yeah, hello. Very excited to be here. I've been listening to podcasts for a while now, and it's great to be as an interviewed person here today. Yeah.
Oh, that is so cool. We are very excited to have you. Even if I'm still working on my first cup of coffee, I'm still super looking forward to learning more about your science and your life as a scientist. So let's start with understanding your current research. So what are you doing? What are you postdocing about?
Yeah, it's a bit hard to answer this question because I don't think right now I have a very specific thing that I've been working on. Well, maybe that makes it easier actually to explain in general terms. So what I do as a researcher is working mesoscopic and nano electronics. So mouthful, so let me try to break this down. Well, I'm a physicist. I'm a theoretical physicist. I do computer simulations. And I work specifically with electronic properties of systems. So that could be also how the electrons behave inside the material, or maybe things a bit more complicated, like a small electronic device. I don't really do things like big electronic components as in computers, but very fundamental, small pieces of devices that do very simple things. So these devices are usually very tiny in the nanoscale, or maybe they have, so that means like a billion times smaller than a meter, 10 nanometers to 1 micrometer. So I do research trying to understand how these devices operate. So sometimes I look at the experimental works and try to understand how they are showing the features that they show, or I try to come up with new phenomena that people maybe will be able to measure in those devices.
And it's all theoretical. You mentioned this is all theoretical. So what are your tools like other than just your laptop, your headphones? What kind of tools do you use? What kind of softwares do you use?
Yeah, actually, that's most of it. I mean, we do a lot of coding in Python in our group,
Mm-hmm.
but I mean, could be any language that you want really. But our group is mostly doing stuff in Python, and one of the reasons for that is that the PIs in my group actually developed a Python package for studying electronic transport in these devices.
Mm-hmm.
So since we already use this tool that is built on Python, we just continue use this language as our kind of default language to do coding. Some of the calculations that we do are very expensive. So what we do is to send to a computer cluster that will perform, because otherwise our laptops cannot do those calculations. And then I usually need internet connection to submit the calculations and let them run for a few hours or so.
Okay. Okay. Interesting. So you write the code on your computer, on your local computer, and then you send it to the analyzers or is there like is it how does it work? Is it like a company? Is it university? Is it where do you send your code to do this analysis or do this testing? Okay, this is the data set, this is my code, run it through. Where are you sending this?
So we have two options. We have a small environment that we use in our group that is also not supposed to do heavy calculations, but we can run it online. So we have our own environment online, and we not necessarily need to write code locally, but we can just access through the browser. We can have a, I don't know if you were familiar with it, and also maybe the listeners or not, but it's just a browser Jupyter notebook. So we just write code in there, and we have access everyone in the group. And then from there, we can also send to a cluster that is, I'm actually not sure if this cluster is in the university, but is a university rented at least. Maybe they rent from a company. I'm not so sure about that. I think is physically in the university, but I cannot assure that right now. Anyway, we sent to this cluster that is from the university, and the university gives access to anyone in the department, really, like doesn't matter well, of course, you need to explain what you were doing in the cluster, but once you tell the university what's your purpose, they'll give you access regardless of where what you are working on. So I think each department have there are computational facilities, and in our case, we have a dedicated cluster to run our calculations.
This is so fascinating. This is a completely different world for me. Because when I was doing research, when I was an active scientist, I was an experimentalist. I was doing experiments in the lab, getting the data, analyzing it. This is so cool that, wow, this is a completely new world and how it works. This is really fascinating. Tell me about your career journey. How did you end up doing a postdoc now in the Netherlands at TU Delft? How did that happen? Give me like your life story.
Well, I'm Brazilian, as you said, and I did both my bachelor's and my PhD in Brazil, in the University of São Paulo, which I think, well, at least in Brazil is the largest one. I think also maybe the largest or second largest in Latin America even. They are everywhere in the state of São Paulo. They were still expanding, actually. When I started my bachelor, they just incorporated the campus that I was studying. And as a consequence, they also created a new course that was engineering physics. And engineering physics as a bachelor program was a very new thing in Brazil. Actually, there was only one other university that actually had a running program on engineering physics. And that got me very excited because, it merged two things that I was thinking about. One was like more fundamental aspects of physics, and the other one was engineering and more like technology-oriented studies. So I found the idea very interesting, and then I started a bachelor's in there. And then I also very early had the good idea that I wanted to at least try to do research. I had contact with a few people that were researchers, and then I kind of got like the idea of it. So I tried to find professors already in my bachelor's that would have me as working somehow with them. And in Brazil, we have this program. In Europe, it's not very common, but we have this scientific initiation program where bachelor students actually work just as they are group members in a lab. It's actually really cool. You have like it's usually funded as well, so you have 1 year long fellowship that you can use to work in any lab, basically. And then I started in this program as an experimentalist, and so I joined an experimental group doing superconductivity. Well, basically, very quickly, a superconductor is a material that has no resistance. You can use these to generate very strong magnetic field. So this group was trying to improve some materials to get even higher magnetic fields. If you make a wire with this material, it could reach even higher magnetic fields. And the reason is that at some point, superconductivity just breaks. When you reach some magnetic field, the material stops being a superconductor and just becomes a regular metal, just like a wire, a copper wire that we have everywhere or something like that. But they were doing something tricky because they were using ceramic materials to make wires, and sounds very weird because like how do you even do it? And the idea is that you would make a very thin powder with it, and you just put on a metallic tube and you just stretch it. So then at some point it becomes a ceramic wire. And I was supposed to characterize this powder. So what we do is we compress this material up to a point that becomes like a pastel or something like that. And then I was measuring it. So most of my job was actually just cutting those samples, and cutting ceramic is not an easy task. It breaks very easily. So at this point, I was like, okay, I don't want to be an experimentalist. I don't want my life to be like that.
How dare you? It's fun, Antonio. Come on. It's a lot of fun.
I'm sorry, that was traumatic. But then I got really interested about doing the data analysis of it and trying to understand how we could estimate the maximum field that those wires would operate by just doing measurements in these tiny samples. And then that made me get more and more interested on the theoretical aspects, and my supervisor just let me study the more in-depth theoretical aspects and gave me some guidance to actually understand better the things that I wanted to. And then I as a follow-up project, and that took a year. And then as a follow-up project, I really wanted to do something more fundamentally theoretical, or at least change fields, because I was very tired of cutting ceramics. And my supervisor was like, okay, but I actually kind of want to work with graphene. I'm actually not so sure if we can make it here. I'm not sure if we have the proper facilities for it, but I really want someone to actually study and try to write something in terms of like maybe things that we could start thinking about. And at this point, I was a more senior bachelor student, and my job became then just read papers, understand and discuss with my supervisor, and also discuss how to actually even run experiments at some point if we wanted. But then again, I got way more interested about the theoretical aspects, and yeah, then I learned how to calculate electronic properties. I got super interested about the papers, and then I kind of teach myself how to do DFT. So for those that are listening, is just a computational method to calculate electronic properties of materials. That's as much as you need to know.
Right. DFT stands for dysfunctional non. What does DFT stand for?
Yeah, DFT
Stands.
stands for density functional theory. So it's a theory that says that you can actually, instead of thinking about many electrons in a system, you can just think about their density. And that makes things much simpler, because then you have the system that has like a lot of information, and just simplify it to everything is contained in the electronic density.
Mm-hmm.
Anyway, then I learned how to do things, and then I was almost finishing my bachelor, and then I was very confused on what to do at this point, because well, it was clear to me that I wanted to do research as a PhD, but I had no idea what I wanted to work with. And then I started just browsing internet and trying to find something. It was really like, well, okay, what can I do? Also trying to check a few programs to see what they would offer. And then at this time also became clear, since I was doing research for so long, that I could also skip a master's diploma and go to a PhD directly. This is not so normal in Brazil. It's kind of same thing as in Europe. Usually most people do a master's, get a master's degree before they go to a PhD. But I could do that if I stayed in the same campus and kind of with the same group. But as I said, my group was experimental, so sounded like a fun idea, but at the same time wouldn't be really a thing to do theoretical research with the supervisor that was not a theoretician. So that's when we partnered with another professor that was in the department that was doing high energy physics, but wanted to try something in condensed matter. And we started working on thinking about things that we could work. And then I started actually a course that is provided by the group that I'm in right now. They were teaching about topological aspects of materials.
No, what is it? I've been meaning to understand it.
Okay,
Again.
so let me.
So let's just go for it. Yeah, now we are in it.
All
So
right.
let's just go for it. Yeah.
Okay, so
No mathematics and physics, though. I want to be able to understand this without having to need a second cup of coffee, Antonio.
all right.
Topological stuff. Tell me.
Materials have these properties that are related to how electrons behave. Okay, so a lot of properties, actually, how they conduct electricity, how they conduct heat, how chemical bonds are connected. Most of the things are actually related to electronic properties. And because of that, you can also kind of like studying electronic properties, you can also understand if a material is an insulator or a metal, for example. But there are different kinds of insulators, actually. There are insulators that are not an insulator in the same way as the air around us, for example, or the vacuum. Those are insulators of the same kind, let's say. But there are different kinds of insulators. And right at the interface of those two insulators, because they are very different, you actually need to transform from one insulator to the other. And that actually creates a metallic region right at the boundary of this system.
Which two insulators? We were talking about vacuum and air.
Yeah, well, so for example, a material that is an insulator now,
Yeah.
which we call a topological insulator.
Mm-hmm.
So now if you place this material in a room that is like surrounded by air or surrounded by vacuum or anything, inside this material is an insulator and outside is also another kind of insulator, but right at the interface, you actually need to have a metallic region.
Oh, okay. So it's like if I have this cup, this is a topological insulator. It is in the air, but on the inside, it is a topological insulator. On the outside is topological insulator, but here
Yeah,
on the surface.
the air we don't call it topological insulator because it's trivial in this sense that is like just a regular insulator. It's a very boring one, let's say, the air vacuum and all those
Right.
things.
So the normal insulator is our air, and topological insulator is our this fancy material, and
Yes.
their interface here is some stuff happening.
Yeah, because well, so insulators are known for having an energy gap, so an energy range where you cannot really have any electrons. Yeah, we have valence band and conduction band, which comes also from the orbitals and whatnot. But now, if you make this topological material, this topological insulator, it has a gap that have a different kind of structure. And then to transform from the gap of this topological insulator to the normal gap of the air or of the vacuum, you actually need to close this gap and reopen it. When you close it, you make a metal. So right at the interface, you have something that is metallic, and deep inside the material, it's still an insulator. And outside it also is also an insulator, but at the very edge it has these weird metallic properties. For example, electrons don't really feel disorder in this barrier because this needs to be metallic anyway, so you cannot really make the metal much worse than it is.
Right.
Kinda. So it's actually very good for electron transport and things like that.
So why do we need this interface, right? Why do we need this topological insulator, this magic that is happening at the interface between the topological insulator and the normal insulator, which is the air? What can this be used for? Why is this important? Why? Can I use it in my phone? Like why?
The interface can be as rough as you want almost, and the material will still have these metallic states. So, for example, you have very, very good electron transport, and you could try to use that to build a material where you have a lower dissipation than you have in another kind of electronic device. So now thinking about actually small stuff, because you cannot really have a brick of a topological insulator. It's not. I don't think that's easy to fabricate. But if you have a very tiny material, you could think that you can actually transfer electrons from one wire to another wire very efficiently, because these edge states are very much protected.
Okay, topological insulators. Thank you very much for explaining it. It did. I think I understand them a bit better now. So thank you very much for the crash course for me and for our listeners or watchers. Okay, so you found a group
Yeah,
that was
yeah. So
topological insulators. Yeah.
yeah,
Go.
exactly. So they were giving an online course on these topological aspects in condensed matter. And we're like, oh, this might be fun. We can actually maybe try to think about a PhD project based on this stuff. That's actually how it went. So I had some experience with graphene and superconducting materials. And we tried to actually understand whether we could use topological properties of, well, actually make those materials topological. So my PhD started like that. And it kind of course, it changed a bit on the way, but I was still studying graphene in combination with superconductors all the time. So yeah, most of my PhD was just studying these nano or mesoscopic devices made of graphene. So for those who don't know, graphene is like the graphite that we have in our pencils is just a stack of many sheets of carbon. Yeah, many layers of carbons. And if you isolate one of those layers, you actually have what we call graphene. So it's just a very thin layer of carbon atoms. And it's also a very interesting material where electrons move very, very easily. And then we were trying to combine them with superconductors to make tiny electronic devices. Not really focusing on any application, but just to study from a more fundamental point of view. So this was during my PhD, and then the group was just starting. We kind of just got the idea and tried to work it out. So it became clear that I need to go somewhere else to get more experience from actually a group doing active research on that. And that's how I came to Delft for the first time. We also had a program that allowed me to do a 1 year internship in a group abroad. So I stayed here for 1 year, and then that's actually how I ended up as a postdoc, because then I came back to Brazil, defended my thesis, and then it became just natural to come back as a postdoc for a longer period and actually do things that were not just bounded by my thesis topic, but to other type of research.
Okay, interesting. So from Brazil to Delft, and then back to Brazil and to Delft, and I think you also spent some time in the US with some experimental group, right?
Yeah, that was more recent. Coming to here, since I had all this experience with graphene and superconductors, I've been was visiting last year a group in Cornell from Professor Vala Fatemi, and they're doing research exactly on this topic, but from the experimental point of view. They're combining graphene with superconductors, and then was tried to help them to design the experiments. They're also just building the group now. Vala is a new professor in there, so he wanted some to build up some ideas and have them in mind when they started running the first experiments.
Okay, this is interesting. So you have had quite a fascinating journey so far, and I think I know you do not want to do like cutting the superconductors because of not the experimental work, but you cannot escape it because you keep gravitating towards experimental groups, or they keep bringing you, like sucking you in. So I won't be surprised that next time you're on the podcast and we are talking about your research, you're like, well, actually, I'm working in an experimental group now. I won't be surprised if that happens. But this is great. I mean, the experimental and theoretical, they need to work hand in hand. I mean, you cannot be isolated.
Yeah, exactly. I was always interested in like interpreting experiments and trying to discuss as well with experimentalists, especially because my department in Brazil was mostly focused on experimental physics. So it became very natural to me to just get contact with a lot of experimental research. And then I now kind of need some experimental background always as kind of a motivation to start a project. Otherwise, it's hard for me to actually feel like I'm doing something that but I really don't feel a lot of attraction for like very abstract research. I like to do something that is related to something that people are measuring or something like that.
Right, yeah, that makes sense. And so that brings to mind my next question, Antonio. You have been involved in a lot of interesting research projects, starting already during your bachelor's, even before starting the bachelor thesis. So this is a tricky, or rather, this is a mean question. If you have to pick one research project that you're most proud of, or the most fun or quirky one, could you pick one and explain it to us in super simple words in the section we call In Other Words? Go for it.
Okay, so I'll actually try with a very new project that the manuscript just came out on archive, and I think I'm just because it was a recent one, I'm feeling still attached to it. I think with time I kind of like forget a few of my papers, and this one is still very fresh, and I was also very excited with how the paper came to be. So what we were studying is a device to do quantum computing, but not the usual way people do quantum computers. So let me first explain what's the usual way to do quantum computing. So our computer have like our laptops and cell phones. They have they operate with these things called bits. So these are just numbers like 0 or 1. So we call these pairs of numbers as bits, and these computers basically do mathematical operators with zeros and ones.
Okay.
And then when I go to a quantum computer, we could also think about having a quantum version of those bits, which we call qubits. Not very creative. But yeah, that's essentially how you kind of do quantum computer. You kind of extend this classical concept to something that is fundamentally quantum, and then things get more complicated. You have some advantages and also some disadvantages. But anyway, that's the way you regularly do quantum computing. But now if you do like a Google search to know what you can actually do with a quantum computer, you find a lot of things like how we can search for new materials, we can search for new, I don't know, molecules, for new drugs, and for, I don't know, the possibilities are many, but one of the things that we could actually do with a quantum computer is solve very complicated systems where electrons interact with each other. And that's usually what happens inside a material, inside a molecule. So that's kind of why you see a lot of those applications for quantum computing, because it's intrinsically very good at solving these specifically tasks. But qubits are not the best way to do that, because these, we're talking about system of electrons, and qubits don't really behave the same as electrons. So qubits are not the best way to do quantum computing if you want to simulate systems with many electrons, because qubits and electrons don't behave the same way. So you could think about building something that behaves way more similar to an electron. An electron is a particle that is called a fermion. So it's a family of particles that behave very similarly, called fermions. So we were trying to come up with a device where you can actually do what we call fermionic quantum computation, which would allow you, for example, to not have these problems, that similarity problems between qubits and electrons, because now we start with something that is way more similar to an electron. And then mapping one thing to the other is actually very straightforward. So we actually did that by, again, combining superconducting materials with the now in this case semiconductors. So there is actually 3 or 4 recent works here from Delft where experimentalists were working on a very similar system where you can actually control very precisely how electrons hop from one very tiny region to another. So you can control how they hop to one place to another. And they could also make the way the electrons hop. You could, for example, make this electron go from one side to the other as an electron, or this electron could transform into a hole. So what is a hole in
Hole is the absence of
yeah, exactly. So you just remove an electron and you have a hole.
Mhm.
And so you can actually control this process very coherently. And when we've learned about it and putting now in the perspective of fermionic quantum computation, we realize that this device has pretty much all the ingredients to build a fermionic quantum computer.
Mhm.
So our this project was about coming up with the very basic building block of what could be a fermionic quantum computer.
Mhm. Mhm.
Yeah.
Okay. Wow. Oh, that is wow. Wow. Okay. Okay. So can we do it? We can, right? The paper.
I'm trying to convince some experimentalists to actually measure, because actually, I mean, the device is pretty much out there. They actually need to add a capacitor somewhere, which that might be tricky for them. We've been discussing about how to do that, but the devices are kind of ready to measure. So I hope they actually are convinced by trying at some point soon.
Okay, so if it goes according to your prediction, what implication will it have? Does this mean that my computer will be, I don't know, X times faster, or my phone will be X times faster, or like what okay, this is really exciting. What, and also very conveniently you're based in Netherlands, which is where ASML is also operating from, I think. So what are the implications that we can expect if it goes as according to your predictions? Like, what will be the implication?
I don't think we'll have quantum computers available as our personal computers anytime soon.
Why? Fine. Best
Yeah,
case
so
scenario. Antonio, we are doing best case scenario here.
yeah, I know, but I'm just trying to be slightly realistic. Sorry, I can also try to imagine a very idealistic thing, but just to give an explanation for people, it's just because you need very low temperatures. to have a quantum computer. Like, and we were talking about like minus 270 or 73 below the room temperature.
Mm, mm, mm.
So it's very, very code stuff. So we cannot just carry in our pockets. But well, say you have like internet access to a quantum computer, and then your cell phone can just be connected to a quantum computer. That I still don't know how it works, because quantum computers are good for specific classes of problems, and cell phones are built to solve another class of problems.
Yeah.
So then also, even in this case, I don't think necessarily that would mean computers running faster, but rather we would be able to solve problems that we're not able to, which I think is not as exciting for people listening, because it's not like you have a better computer, but scientists will be very excited about solving their own problems in this computer. So remember the cluster I was talking about in the beginning, maybe actually in a few years we'll have a quantum computer running things that we could actually use to solve specific research tasks.
Mm-hmm. Yeah, it will basically accelerate the advancement of science and any sort of data analysis or computing to some extent, right? It doesn't have to be personal computer, personal laptop, personal phones, or anything like that, but basically advancement of science, or with the data analysis, so to say, it basically brings us so much faster to the next step, or to develop technologies which are needed, which can then make the computers faster, and like personal computers faster, or our phones faster, or so. But this is really, really interesting. So next time, Antonio, yes, I'm going to bring you on the podcast next time as well, another time as well. And next time, then you can tell me how realistic, how did the experiments perform, and what worked, what didn't work, and then
I hope so as well. Yeah. Maybe that's how I end up inside the lab. They would try to bring me in.
Exactly. Yes. See, you're
No,
gonna
I'm kidding. I'm not doing this, but I hope I can convince these colleagues to actually do something similar.
that sounds amazing. So Antonio, I have the feeling that you love the research part of being a scientist. Research does not mean on in the lab. It can, in your case, it means on your computer, definitely.
Mm-hmm.
But what else do you like being of what else do you like about being a scientist, other than the science and the research aspects itself?
Yeah. Okay. So. Yeah, I actually think that as of course there are problems in the career itself, and I guess we can talk about that later on. But I really like the way we have freedom to actually kind of choose the problems that we're interested in. Of course, we're somehow constrained by like getting funding and things like that, but it's much less constrained, for example, than working in an industry that is focused on delivering a product. We can now actually figure out things that we're interested about, and actually try to build our research path based on our own interests, and not only on things that people are asking us to do. So this is one thing that I really like, and throughout my career, that was very fundamental. As I said in the beginning, was an experimentalist, and then I had the option to actually do theoretical research and learn from it, and that's how I actually got here. So I'm also very happy that I had this chance before. Mm-hmm. And yeah, so this is one thing. The other thing is that I really like to work with students in general. I really like the teaching aspect of it. I like to have like interaction with younger students that come sometimes with no clue what they are doing, and then you have to break down their projects in very small pieces and explain them bit by bit what they're doing. And then you see this person that had no idea what was doing at some point is discussing like very complicated physics and bringing you papers that you never heard about, and you're like, oh wow, that's great. Like, you know, have these feedback from the students that they're actually growing as professional researchers is something that I really like. Also, the teaching aspect is something I don't know. Most of my friends don't love to teach, but I actually had a lot of fun when I had to. And I think I really like interacting with students in general, not only in the research environment, but also in classroom. Yeah.
Okay, okay. I mean, you are a great teacher. I have to say, in my experience with you of less than an hour, I already understand topological insulators and your research. So you are a really, really
Okay, good that I made it at least somewhat clear. It's hard to break those things down sometimes. Like when my parents try to understand what I do, I usually have a very hard time to try to explain those things. But we also need to do this because otherwise people will never really care about what scientists do. So we need to somehow communicate in some sense.
absolutely, totally agree. So, okay,
Yeah.
let's talk more about then what can be improved. So, if you had three wishes to improve your research experience, Antonio, what would you ask for? And I'm not promising anything here, okay?
Yeah. All right. So I think this one is very common in the podcast. Having a more stable career for postdocs, I think, is one of the things that in academia really needs to be fixed as soon as possible. I think that the psychological implications of putting people in short contracts, it's actually terrible for academia, and I really wanted these to be solved, but somehow I really don't have any clear way to solve it. But it would be really nice if people taught more about how to actually solve these, because I see a lot of people really talking about the problem itself, but I don't see many discussions on, okay, what can we actually do to improve the life of these people. And as I said, I have no idea on how to solve it, but it would be great to have these. It's not something that I really faced, but here I'm actually in a longish contract for a postdoc. But I see my friends around, and they are all stressed about moving and having to find a job in the last minute because they cannot really extend for sometimes even for a few months is a bit hard for them to extend. So this part is very annoying, and I think academia should really be more involved to keep those people inside academia. Otherwise, these people would just leave, and they are usually very good talents, and we just lose them.
Absolutely. Yeah.
Yeah.
Is your first wish a better job stability?
Yeah.
Two more.
So second, I think, well, this is something that I kind of felt more closely, which is geographical bias in academia in general. That can mean a lot of things. For example, I had referees really attacking me personally in my papers, which I think is something that people would not do. Yeah, exactly. And I think I would not face these if it was not geographical bias. Also, I don't know, even visibility itself, like you see sometimes, and I'm not saying that people have bad intentions, but you just sometimes see people focusing on following a specific research group, and they barely care about the other research groups around the globe that are doing also similar research and maybe just as good, but just because they're not in the very famous university, people just don't care about them.
Yeah, yeah.
So
geographical bias could mean like basically a bias, just like
yeah, of course, yeah. But in
bias.
general, bias would be perfect. Yeah, I'm saying geographical bias just because something that I experienced, but the bias in general would be. I mean, there is no reason for us to evaluate people based on
I'm
where
sorry
they come
to hear
from,
that.
or yeah.
I'm really sorry that you had to experience it as well. I mean, I think every person who is not from the first world countries or whatever has at least one story of how they had to face situations which they wouldn't have to face if they were from a different part of the world, or they look different, or they sounded different. So I'm really sorry
Yep.
to do that. So first is the stability, second is just equality. I think it's just
Yeah. That would solve not only the problem that I listed, but many others. So it would be great, actually. Equality would be amazing.
yeah.
And then the last one, I guess, would be a better open science culture in academia. I guess it's a bit more specific because we do see people I think open science became actually a big thing now in Europe, at least. You can actually see that even to get the funding, you need to have some open science plan for your research, and you have to disseminate these somehow. But I think we're very far from any reasonable situation. Let me just give you one example. Say you were publishing in one of those glossy journals that allow you to have an open science paper in there. Then you have to pay 10,000 euros to do that. That's ridiculous. Like, why would you need to pay 10,000 euros to make a PDF online? That's absolutely ridiculous. And there are actually many initiatives out there that are actually trying to change these and actually make like full open science journals, for example, where you don't need to pay both to publish and also to read. But not only that, but also, for example, sharing code and data. I realized that every time that I try to reproduce a paper, I have a very hard time. And I also find mistakes in people's papers that would solve it if they actually made code available for referees to check and maybe give feedback on the code itself.
Yeah, absolutely.
So that would be great also for reproducibility of research. And so yeah, I think open science in general would also help equality, because then people from poor countries would also have access to things that they usually not necessarily have, but also for their reproducibility and also to make better science itself. I think it's very important for us to take more steps on sharing more information and not be just afraid that another group would have our data. This is whatever, like
yeah,
if you are doing creative research, you don't really need to worry about those things. So
yeah, absolutely, absolutely. I completely agree with all three wishes of yours. So stability, equality, and open science. That's just like, it sounds very simple and it sounds very basic that, yeah, obviously you need it, but I think we need to keep highlighting it, also to keep the conversation going and also towards finding solutions. This is very, very important. I totally agree. Totally agree. So, Antonio, this has been fantastic. But before I let you go, I'm going to ask you one last question.
Okay.
What can the followers expect when you're tweeting from the Real Scientist Nano Twitter account, which is the second part of this material science project of ours? So in your week on Real Sci Nano on Twitter, X, or whatever the fuck it is called now, what can the followers expect?
Yeah, so I'll try to dive a bit more on those physics things that I try to stay slightly away during the podcast, because I don't want to dive too much into the details. So I'll try to give a more intuitive explanations of those things. And I hope as well I share a bit of my daily life as a researcher. So I'm also planning on do a bit of it. Yeah, I think that's essentially my plan. Try to explain a bit more my research in terms of more physics, like give more physics concepts to the audience, and also share a bit of how my life works and how I realize that not many people know how a theoretician works. So I'll try to share a bit more how is my daily life as a theoretician.
Absolutely, absolutely. And in addition to the science, if I may request a few things, please also tell us about the university you did your bachelor's in, because I have no idea how the labs look like or how the university building looks like. I don't know the campus, anything at all. So if you are able to get those pictures and share them with us, that would be really cool. And of course, also with Delft and your life.
Yep.
Just pictures of your life as a scientist. Just
okay.
Life as a scientist. That would be wonderful. So thank you very much, Antonio. This has been wonderful. Looking forward to having you now on Real Scientist Nano Twitter account. Thank you very much.
Yeah, thank you very much for the opportunity. It was great to talk to you.